Okay, so how is everyone today? Good? All right. So last time we had finished. The place where we finished is we had started talking about a game called Guess the Natural. Oh, come on now. All right, that's better. We had discussed that game, Guess the Natural. So it's a two-player game. So let's write down those rules again. So this is the Guess the Natural game. Guess the Natural. There's two players. One of them will refer to as the oracle. So the oracle because that's the player that knows the answer and is able to respond to your questions. So so this oracle knows the hidden n, which is a natural. So, you know, if you're playing this with two people, then what it is this is the person who thinks of a number but doesn't tell you what it is. Okay, so then the true number is n, but it's unknown to the other player. What the oracle is, so the oracle is a function f from the naturals to the set -1, 0, 1. Okay, so it's a function, and so the way it works is like this. So the other player, suppose that the other player makes a guess. They guess m in the naturals, and then the oracle responds with one of those three outputs. So in the case, so if f evaluated at m is -1, what that means is that m is too small. It is not correct, and furthermore, it's too small. So then m is less than n. Okay, so if f of m is 0, so the player's guess is m, and suppose that that the oracle responds with 0, that means you got it. Okay, so that's how to interpret that. And then finally, if the player guesses m and the oracle responds with +1, then what does that mean? Yeah, it means that m is greater than n, which is, you know, in the game interpreted as that's too big. All right. Good. So besides this kind of idea, the oracle is also counting. Your number of guesses. Really, the number of evaluations. So the way the assignment is going to work is that I've written the oracle function. So that's something that I wrote. And reality, what I actually did write is I wrote a function that sort of makes an oracle. Okay, so then you can call a function to make an oracle, and then the result will be another function. Did you have a question? Yeah. Thank you. Good. So there are. Here's. Strictly speaking, you don't need to know exactly this next thing I'm going to say, but it's a nice thing to know. So in the first place, you can look at the function that makes the oracle. It's not like a secret. You can just look at it. It won't. Reading the code of how it's made doesn't give you any insight as to how to beat the game. So go ahead and look at it. But there's a function. Well, let me make an example. So you know how we've got a function called cosine? You know? So its full name is cosine, like that. But of course, how do you write it? COS, right? So it's written. When you're using it as a function, you write it cos. Okay, similarly, there's a function called Signum. Signum, and it's written like this. Depends on the textbook, but I'll just write it as SGN. Its signature is reals to -101, and its definition is SGN of x is -1 when x is negative, 0 when x is 0, and 1 when x is positive. So you can kind of think of it like it's a function that you put a real in. You put a real in, and then out comes basically the sign of that real. So if the real number that you put in is negative, out comes -1. If the real number you put in is positive, out comes +1. And if you put in 0, out comes 0. So that's because that's the definition of the Signum function. The oracle can be written more or less like this. You can say, and the function does say that f of m is going to be SGN of well, you tell me. What do I have to put in there? N minus m. Okay, so let's see if that's right. So if m is too big, if m, your guess, is too big, then what is the output supposed to be? Right. So if m is too big, it should be +1. So is this one right? No, it's not right. How do we fix it? The other way around. Which is to say that, all right, if suppose the true answer is 10, and someone guesses 5, then this would be 5 minus 10, which is a negative number, and so the signum of that would be -1. And if someone guesses exactly the true answer is 10, someone guesses 10, then this is 0, and then the output will be 0, and then if the true answer is 10 and someone guesses 30, then this will be 20. The signum of 20 is 1. So the oracle is not exactly this, because you also have to, it also has to keep track of how many times did you guess. So, but this is part of it. So, the number of guesses will be counted, and it'll be your job to figure out how to shave off as many guesses as possible. So if you've done it more or less right, then you could get an error that says that that you guessed the correct number, but you did it in 36 steps when you should have done it in 35. Could be something like that. If you've done it more or less right. If you've done it really not right, then it'll be something like you found the correct answer, but you used 4 million steps, and only 20 were necessary. You know, something like that. Okay, fine. So the place that we got to last time, that's the oracle player. Then we have the guesser, the one who guesses. And we discussed a strategy for how to go about making your guesses. And specifically, we were considering the situation. What if the oracle was telling you, I'm thinking of a number between, say, 1,000 and 5,000? And then if it's me, if I'm the oracle, then you say, is it 2370? And then I say, you got it. Got it. Okay, but ignoring that silly business. If you say, I'm thinking of a number between 1,000 and 5,000, then what's the optimal strategy? Guess 3,000. Why 3,000? It's the midpoint, right? It's the midpoint. So let's be clear about why guessing the midpoint is going to be a good strategy. So, just for sake of just illustration, I'm going to draw 7 points here. One more. So you could think of this, if you just want to put definite numbers on it, you could say that this is, 20, 23, 24, 25, 26, 27, 28, 29. Okay, so then, so it would be like saying I'm thinking of a natural between 23 and 29 inclusive. So then you can compute the average of 23 and 29, and what's the average? It's 26. So we're going to guess. We're going to guess this one right here. So the oracle is going to respond with just one of three responses, right? So one of the possibilities. So if we're saying that this 26 is going to be M right here. So if it is the case that f of 26 is -1, then, well, by virtue of the output of the oracle being not 0, that means that the answer is definitely not 26. Because if it was 26, the oracle would have responded with 0. So it's definitely not 26. But so we can eliminate 26. But I claim that in fact we can do better. So what? Yeah, because if 26, to say that for the oracle to respond with -1, that means 26 is too small. So that also means 25 is too small. Okay, and in fact everything to the left is too small. So notice that by virtue of making that guess and receiving a response of too small, that means that in fact we eliminate half of all possibilities. Okay, in fact, because there's an odd number of choices, we eliminate just barely more than half. Right? We eliminated 4 out of 7. Interesting. Okay. So that means that there now from that point on, there's only three choices. All right. What if the oracle responded? So we went through that hypothetical. What if the oracle responds with 0? And what does that mean? Yeah, it means you won. You won the game. Okay. It could happen. Finally, the only other response that the oracle could give is to respond with 1. Okay, so if the oracle responds with 1, what does that mean about your guess? It was too big, so in particular 26 is not the answer. And what else? Yeah, neither are any of these. So, you know, you could just get, you know, real lucky, and then the oracle says, oh, you got it. Hey, 3,000 was the answer. Or you eliminate essentially the left half of all possibilities or the right half of all possibilities. So you either get it right or you eliminate half of all possibilities. Okay, so does everybody understand the reason to guess the midpoint? So now, if you know, I only drew 7 points just out of just to make something easy to draw, but you know, in principle there could be 7 million points. And you might ask, do you always want to guess the midpoint? You know, maybe instead of guessing like the 50% mark, maybe why not say like the 75% mark? You know, because you know, you still have the same 3 outcomes. Is that you either get it right, or you eliminate the left part or the right part. So then, if we say 75% going to the right, that would mean that if the oracle responds to your 75% guess, and they say that's too small, then you eliminate 75% of all the choices, right? But if the oracle responds and says that that's too big, then what? Yeah, you eliminate 25%. But you know, it's still an interesting question as to should we always go with 50% so that we always eliminate half? Or are there good reasons to maybe say always guess like 55%? You know, what would be best? And so in answer to that kind of line of inquiry, for the purpose of this exercise, we're always going to guess the midpoint. But I want you to think like, wait, is guessing the midpoint really the best thing that I can do always? Maybe there's some other thing that I could guess that, for you know reasons mathematical, might be even better. So, just as a foreshadowing of that idea for future topics that we probably won't get to in this class, but you might get to. Well, if you take numerical analysis, you will get to it. You'll have to do this kind of searching thing, and in fact, you won't search with the midpoint. It'll in fact be better to search instead of at the 50% mark to search somewhere nearer the 61% mark. And you know, that seems kind of specific. 61. Why 61? Does anyone know why? It's really quite incredible. Believe it or not, it has something to do with the Fibonacci sequence. It has something to do with the Fibonacci sequence, and the question, the particular thing that you're doing with has to have a certain kind of structure. But you know, the Fibonacci sequence is related to the golden ratio, and this 61% is in turn related to that. Okay, so interesting. Good. But now here's a twist on the guess the natural game. The twist is that the oracle is not going to tell you the interval. Rather, the oracle is just going to say, I'm thinking of a natural. That's it. Not, I'm thinking of a natural between 1,000 and 5,000. Just, I'm thinking of a natural. So the oracle does not give the lower and upper bounds. So that means it's going to be on you to figure it out. So let's imagine, right? So what's a good strategy? How could we establish some lower and upper bounds for ourselves? What do you think? Any ideas? And by way of, kind of big hint, so the way, once you have bounds, once you have them, then what we're going to do is we're going to start cutting in half the number of choices at each step. And to establish the lower and upper bounds, we're going to basically do the opposite, kind of. Very good. So let me. I'll give a demonstration of what was suggested. So I need a volunteer to be the oracle, and I'll be the guesser. So can I have a volunteer, please? Someone? Otherwise, I'll point. You want to do it? Okay. So then, now, for the purposes of demonstration, I want you to, don't tell me, but select a number between 100 and 1,000, but don't tell me. And, understand that's just for demonstration so that the game doesn't go on for too long. Okay, and I don't have to do lots of really silly, complicated arithmetic. Okay, so you have one?
I think so.
You have one. Okay, so I'm going to start guessing, and then I'm going to record your response. So, and you have to make one of three responses, either too low, correct, or too high. So how do you respond to one?
Too low.
Too low. So how do you respond to two?
Too low.
Okay. To four?
Too low.
Too low. So it doesn't really seem that awesome, right? This is going to take forever. 8?
Too low.
16?
Too low.
32?
Too low.
64?
Too low.
128?
Too low.
256?
Too low.
512?
Too high.
Okay. So, interesting. At first it kind of seemed like I was going a little slow, right? At only there I was at 32, right? Or there, I'd only made it to 32, but already I'm at 512. And so how many steps? That's 1, 2, 3, 4, 5. That's 10. So then, if I in 10 more steps, I'd already be at 1 million. Okay, and or nearly 500,000, and at on the order of 30 steps, I'd be in the billions, and then on the order of like 100 steps, I'd have a number that's more than the number of protons in the universe. That's a lot. So this means something. So I was asking questions about all of these, and then finally notice that we had this transition from -1 to 1. Now it had to transition away from -1. It didn't have to transition to 1. What else could have occurred? What is it? I'm sorry, I couldn't hear. Oh yeah, 0. Yeah, could have been a 0, which just that would have meant that that the oracle, the hidden number that the oracle had would have been a power of 2. So evidently it's not. Right? But this sequence of events is telling us a lower and an upper bound. So what's the lower bound? It's not 256. It's 257, right? Because 256 was eliminated by virtue of the response -1. So the lower bound, if you like, calling it A, is 257. And also, we know an upper bound. What's the upper bound? 511. So this we had to go through this transition. We had to have, because after all, the oracle selects a natural number, and then it's fixed, right? And now this is an increasing sequence, and it's unbounded. Okay, and in fact, it increases quite rapidly. So in a relatively small number of steps, we have to meet or exceed whatever the oracle is thinking about. So now, brief mention of realities. So of course the natural numbers are unbounded, right? Which is to say that no matter what natural number you say, you can always add one more, and that's a natural number too. A natural number also. And an example of exceedingly large natural numbers is something like there's a number used in a real legitimate math proof called Ackermans number, and Ackermans number is like a number that's so large it's like silly how large it is, but nevertheless it was used in a real math proof. And to give you some idea about just how large that number is well, if you wrote a 1 with 80 zeros in it, right, 1 and then 80 zeros, that's approximately the number of protons in the universe. So that's a lot. Okay, but I think I could probably write it in the space provided here. Like 10 by 8. Yeah, I could do it. But Ackermans number is a number that's so long that if you were to write more or less hand-sized numbers on a piece of ticker tape, just a long sheet of paper, that sheet of paper would extend like all the way to the sun and back. So it's a big number, and it's a natural number. So now, fine, that's kind of silly, but okay. Now the machine, the computer, can only represent numbers. It can't represent numbers generally as big as Ackermans numbers. Too big. And in fact, more or less, you can kind of think that the natural numbers that it can represent are basically numbers that are representable with like 64 bits. Now, it can do more than that, but generally speaking, we'll cut it off there. So like the largest natural that we can easily deal with in MATLAB is 2 to the 64 minus 1. Which is a big number, but it's not infinitely big. So, good. Now, I'm going to call this the up phase. Just to call, the reason to call it up is that now here's where, sort of going, the numbers are potentially getting quite big. So they're getting bigger and bigger and bigger until we hit this transition, and now we've established bounds. So now I'm going to do the next phase of the game to demonstrate how it works a little bit, and then we'll move on to something else. So A, B, M, and F of M. So do you still remember your number? Okay. So those are the lower and upper bounds, respectively. So these are both odd. They're both odd, and as a result, their sum is even. So when we divide by 2, so when you divide by 2, the result will be natural again. But when you're doing this, generally, if it's the case that 1 is even and 1 is odd, then their sum is odd. And when you divide, the result won't be an integer. So it could be something like, if the lower and upper bounds were 3 and 11 respectively, then no, those are both odd. Rather, 3 and 8. You add them together, you get 11. Divide by 2, you have 5.5. Should you guess 5.5? No, because 5.5 isn't a natural. Okay. And the oracle is a function from the naturals to negative 1, 0, 1. So rather, you need to round, and the rounding that we'll do will always be floor for this exercise. So we'll round down, so like 5.5 down to 5. All right, but these are both odd. So then I'll find the average. So that'd be 384, so that's going to be my guess. And then I ask, how do you respond? Too high. All right. So that means that I'm going to have to continue, right? Because I didn't find it. But that does tell me how I can modify what I know. So what's the new lower bound? 257, right? It's the same as before. Nothing changed about that. What's my new upper bound? 383. Why not 384? Yeah, we just got finished saying that 384 is too big. So 384 is not the upper bound. Okay. So then now I make a new guess. Okay, so my new guess is 320. Too low? All right. Okay, so then what's my new lower bound? 321, right? Oops. It couldn't be it couldn't be 320. 320 was already said to be too small. And the upper bound is unchanged. How many choices are there now? No, something's not right. I had to have made an arithmetic error somewhere. 57, blah, blah, blah. This one. 357 plus over 2, 320. You said too low?
Yeah.
Something's not right somewhere. Something's not right. Can anyone see where I made an arithmetic error? 357, 257. $384, you said too high. That's still that. 384, 257. Yeah. Something's weird. Oh, no, wait. No, it's right. Ah, my brain. Sorry. Okay. No, here we go. Fine. How many options? How many options are there? No, there's not 64. There really are 63. Now, why are there 63? Sorry, my brain was just like, I don't know what happened here for a second. So, how do you tell how many options there are, by the way? Yeah, you're going to have to subtract those two, right? So you can imagine that you've got, dots labeled 321, 322, 333, all the way down the line, right? Then you could just shift them all over to 0 so that the first one is 0, which is to say you can subtract 321 from that number. And then what do you get if you subtract 321 from that? 62, right? But the number of choices is actually 63. Why? Because which one? Right. So which is to say that it starts counting at 0. How many numbers are there when you count up to 5 starting at 0? 6, right? Okay, so then there's 63 choices. Good. How many choices were there here? 127. And how many choices were here? 255. Okay, what are all these? What are all these numbers? Powers of 2 less 1, right? So there's 64 choices. 63 choices. In the next guess, I'm either going to get it right, or there will be how many choices left? 31. Okay. So 321 plus 383 over 2. So my guess is 352. How do you respond? Too high. All right. So then 321 and 351. Right, so the difference of those is 30, and then add one more for the leftmost point, 31 points. So then 321. So my guess is 336. How do you respond? Too high. Too high. Good. 321. 3. Oh well. So then that's too high. So then 3, 2, 1, and then 3, 5. No, 3, 3, 5. So that's 15 choices. Okay, so my guess is 328. Too high? All right. So 321, 327. My guess is 324. Too high. All right. So 321. What am I looking for? 323. Okay, so how many choices are there now? There's 3 choices. So I claim that in fact, how many more guesses are necessary? I don't think there's 2 guesses necessary. I think I can come up with the answer with 1 guess. Okay, so some of you I see heads nodding, but if you can't see it yet, think about it for a moment, because I don't want to spoil it for you. It's better if you see it yourself. If there's 3 choices, if there's 3 choices, then why should it be the case that I need exactly 1 more guess? Right, so let's consider. There's 3 choices. Suppose I will guess the one in the middle. Okay? The oracle could respond with, that's the correct guess, which means I need make no more guesses. The oracle could say that that's too high. And if there's 3 choices and I guess the midpoint and the midpoint is too high, how many of them do I eliminate? 2 of them. And then how many are left? Just the 1, right? And symmetrically if the oracle says too low. Okay, so then how do you respond? Too low. That means that since that was too low, that means that 322 is too low. So the lower bound is 323 and the upper bound is 323. And I need not guess any further. Right? Good. So I'll refer to this as the down phase. Good. So the assignment, more or less, is for you to write a function that does this. And there's a few cute little corner cases that you have to think about. Like, for example, if it comes down to 3, if it comes down to 3 choices, then if it comes down to 3 choices, it only takes 1 more guess, right? You don't make another guess, right? So if it comes to the point where someone says, I'm thinking of a number between 2370 and 2370, you shouldn't make a guess anymore. Any questions about it? Yes?
Why did you pick powers of 2?
So by way of example, I could say something else. I could say, maybe I'll address your question like this: why not powers of 3? Maybe.
Right.
Okay. So then, of course, powers of 3 is also an exponential sequence, and of course, you will eventually transition from negative ones to something else. Of course, you will. Now, when you do that, notice that the distance between 2 consecutive guesses is always a power of 2. Okay, and then because like the distance between those 2 is 128, the distance between those 2 is 256, etc. And then when you get rid of the midpoints, the endpoints, you're basically the interval is of choices is going to be a power of 2. So then similarly, for the same reasons, if you guess powers of 3, the intervals are going to be bigger. It'll be the difference between 2 consecutive powers of 3. On average, it'll be bigger. Because it could be the case that the oracle the hidden number happens to be a power of 3. And then you wouldn't even have to do any of this, right? So on average, when you're doing powers of 3, the intervals are a little bit bigger. Also, if you're doing this part in using powers of 3, you might think, well, why not this part in powers of 3? So you could cut the population instead of into 2 parts, you can cut it into 3 parts, and then guess say at the 2/3 point. But then you have the same kind of problem that we already talked about, that you're either going to eliminate 2/3 of the population or 1/3. Or you get it right. That's possible too. So in answer to your question, I'll say it like this. As a general rule, this doubling and halving is going to work very well in practice. For specific problems, if the problem has enough of a specific kind of structure, in fact, it can be better to you can do better than halving. But on this specific exercise, it is a hard requirement that you have to do it with doubling and halving, because in order to be correct, I'm counting the number of guesses and what guesses you make. So if you do it with instead of 50%, if you do it with 51%, then it won't be right. Other questions? Okay, so then now, all these functions that we've done this semester that are somehow that are doing a repeated process to do something, like multiply, like multinar, or like that one where you're repeatedly guessing over and over again. They all have the property that they will converge. It will happen. Okay, meaning that the function you get it started and it's going to terminate. The process is going to end. So to give you an example of to give the reason, to give the name to why that's occurring and why we can always depend on it to occur, the name of it is called the well-orderedness. Well-orderedness property. Of the naturals. Okay, so specifically, here's the statement of it. Every nonempty subset of n has a min. And then, in a in different contexts, in different textbooks, the language might be instead a least element. Okay, so for example, here's a set. 23, 70, 20, 18. This is a subset of the naturals, right? Because all those numbers are natural, and as a result of that, the min of A must exist. And because that's such a simple set, you can just read it off for me. So what is it? It's 18, right? Did you have a question?
Yes. To establish this on the natural, do you need the axiom of choice?
I'm going to, well, it depends on how you're going to construct it, but generally speaking, this is taken to be an axiom of the naturals. When you're going to construct the naturals like from scratch.
Well, can you prove that it's true for every subset without the axiom of choice?
I'm going to have to get back to you on that one, because
I'm just going to say no problem.
well, I mean, I don't. I'm going to take the position that I don't want to take a position without having thought about it. I don't say yes or no. But generally speaking, the axiom of choice is a slippery thing, and you have to think carefully about what it means in every context. But at any rate, we're taking this to be an axiom of the naturals. So this set here has a minimum. All right. So then I could say, so that being the first and the second, I could say something like this. I could say, let T be the set of even naturals? So in the first place, are there any even naturals? Yeah, there are, right? Like 8. So that means that T is not empty. It's not empty. Because of the well-orderedness property of the naturals, therefore, it must be the case that T has a minimum. So you should be able to tell me what is the minimum of T. It's 0. Now, lots of folks are a little bit disturbed. 0. Is it really even? Yeah, it's even. So we'll do 2 different reasons for why it's even. But right now, I'll just remind you that to be even means that the following kind of grade school idea. 18, the number 18 is even, because if I were to put 18 M&Ms in front of you and say make groups of size 2, then how many such groups could you make? You could make 9 such groups, and when you're done making those 9 groups, how many will be left over? 0. The fact that there's 0 left over is the reason why 18 is even. That's the definition. Now, I have just put a pile of 0 M&Ms in front of you. Please break them into groups of size 2. Now that you've done that, how many are left over? 0? As a result, 0 is even. Okay. So, fine. Good. So now, here's a problem. I could say, let E be the set of all n in the naturals, such that n is a giraffe. Now, how about this? The minimum of this. Well, in the first place, are there any giraffes in the naturals? I need another F in there or something. Something's not right about that. So this is undefined, right? This is undefined. Is undefined because why? Because E is empty. And the way that the typical way to denote the empty set is with a phi, a capital phi, like that. All right. So then, to make sure that this is sort of clear, and to make sure you can catch this kind of slippery notion, here's something. Are you aware that UTD has won every NCAA National Football Championship that we've ever competed in? Did you know that? That's amazing. In fact, our football team has been undefeated since UTD opened. We've never had a defeat, ever. That's incredible. That's better than Alabama, right? So are these true statements? Yeah, those are true statements. But you've got to understand that means like mathematical truth. Now you might reply by saying, well, it's kind of silly, and I don't dispute that. But nevertheless, it's true. And the reason why it's true is because if you were to say, I think it's false, then I would respond by saying, oh, please show me the game that we lost. And your inability to produce such a game means that the statement I'm saying is correct. And that's disturbing. Of course, the reason is that we just don't have a football team. Yes?
That doesn't mean maximum comfortability?
No, rather what this is about vacuity, right? So, which is to say that this... So I'd be really happy to discuss the guts of set theory, but in the end, I'm telling you, the answer is it's vacuity. Is that any statement that you make about the elements of the empty set is automatically true. For example, just as a funny story, in some math books, and when I was an undergraduate taking analysis, the empty set was defined as the set of all green-eyed lions. The reason being, okay, is that because of genetic reasons that I'm not really privy to, evidently it's not possible for lions to have green eyes. So the empty set is defined like that. So is it the case that every element of the empty set is a green-eyed lion? Yeah, vacuously true, because there aren't any elements in there. So they're all green-eyed lions. They all are. It is also the case that concerning the empty set, all the elements in the empty set represent wins for a UTD's football team. Same kind of reason. It's vacuousness. Good. So now this property is the reason for things like this. So when we defined this function molt in R with signature naturals cross reals to the reals with formula molt in R of n and x is 0 when n is 0 and x plus molt in R of n minus 1 and x. So otherwise, so when doing this, if you're asked to compute, say, molt in R of 23 and 70, like that, then what I want you to observe is that the first argument is 23, and then we'll apply the second clause, and we'll get 70 plus molt in R of 22 and 70, right? And then we'll get 70 plus 70 plus molt in R of 21 and 70, etc. And what I want you to observe is that this first argument is counting down. It's 23 and then 22 and then 21 dot 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 all the way down to 3, 2, 1, 0. But at all times it's natural. So what I want you to observe is that this first argument concerning the repeated calls to molt in R, concerning those as a set, the set of numbers, the set of naturals that are 23, 22, 21, etc. So is that set non-empty? Yeah, there's elements in it. Is it a subset of the naturals? Yes. And therefore, the well-orderedness property holds, and there must be a least element. So what's going to be the least element among those? 0. And that's why we know for sure that this process will terminate. It has to terminate because of the well-orderedness of the naturals. So now, if someone asks, I need you to evaluate the logarithm of negative 12, then the correct way to respond, the correct way to respond would be to say no. Negative 12 is not in the domain. Similarly, if I was to ask you, if I were to ask you to do this, molt in R, and say negative 3 and 70, something like that, then the correct response would be for you to say no. Negative 3 is not natural, so I refuse. That's in MATLAB. That's what assert is giving you. That's the way that you're saying no, I refuse. But suppose that we suspend that for a moment and we just think, I'm just going to try. I want to just see, follow this thing wherever it goes. Then just following this rule, then it would be 70 plus molt in R of negative 4 and 70, right? Because you're always decreasing the first argument by 1. Then it would be 70 plus 70 plus molten R of negative 5 and 70. Okay, so notice that concerning the set of first arguments, so far it contains negative 3, negative 4, negative 5. So is that set non-empty? Yes, it's non-empty, so that's good. Is it a subset of the naturals? It is not. Therefore, we can have no expectation that there should be a least element. It's non-empty, that's good, but it's not a subset of the naturals. So obviously, I think, negative 3, negative 4, negative 5, negative 6, it's unbounded below. It's going to keep going. So as a result, if you could think of it like this, if you wrote this function more or less in MATLAB, but you didn't have the asserts, that would mean that if I called your function with these arguments, negative 3 and 70, and that's the function that you wrote, it would just go on forever. It would never stop. Okay, interesting. Any question so far? Okay, good. So all of the things that we've done, all the functions that we've done, in the end, they're guaranteed to terminate as long as the arguments are in the domain, and you've programmed it correctly. They must terminate, because in the end, you can associate all of those executions to a non-empty subset of the naturals, and therefore there must be a least element, and therefore it must the process must terminate. All right, good. Now I want to make sure something is clear, and that is the following. So how about that set we were just looking at on the previous page? Negative 3, negative 4, negative 5, negative 6, ... Okay, concerning viewing that as a subset of the integers. So is it non-empty? Yes, it's clearly non-empty. Is it a subset of the naturals? It is not. Therefore, we should not expect that it has a least element. And in fact, if we ask about the min of A, then how about it? There is none. So this is undefined. There is no such element. All right. Now, if if it was just those, without the ... without the ellipsis, then if it was just those three elements, then that's non-empty. It's not a subset of the naturals, but yet it does have a least element, right? The least element is negative 5. Okay. How about this one? How about the set 23, 70, construing this to be a subset of the reals, which is to say this one. So does that set have a minimum? It does, right? It's 23. All right, but what about this set? Which is to say the same interval, but I delete the point at 23. So how about this one? Does this one have a min? So does it have one? Does not. Now, where concerning just the stuff that we're talking about on this page, that is in this region, that is to say the well-orderedness property, we have no expectation that there should be a minimum. Now, it's nice that in this case there is one, and it's 23, but it's no surprise that there isn't one here, because after all, this isn't a subset of the naturals. To be clear, 23 couldn't possibly be the min, because well, why not? Why 23? Why can 23 not be the min? It's not part of the set. to be minimal, it must be the case that in the first place you're in the set, and in the second place all other elements are greater than or equal to that one. So you might say, I'll just move over just a little bit. I'll get some point that's just, you know, like right next to 23. You know, maybe like that one is the minimum. Okay, but that couldn't possibly be the minimum, because you know, if you take your calculus binoculars, your calculus eyeball, and take a really close look there, then at some scale, you know, that red arrow is like enormous, you know, like this. And that point, that's not the minimal point, right? Because we could, you know, this one right here is in the set, and it's even less. And of course, that's true no matter what point you select to the right of 23, because you can always move half the distance to 23. So it couldn't possibly have a min. Nevertheless, this next thing I'm going to say doesn't have anything to do with where we're going. But this is a good place to say it. So this set has no minimum. This one that's open at 23, it has no minimum, but nevertheless it has a something that's mathematically important, and that something is 23. So what's the name of that something that this set does have? Starts with I. It's infimum, right? It's infimum. So to sort of describe that, what that means is that if we consider this set right here, so this is 2370, like that, then a number is said to be a lower bound of a set. So like, for example, here's a number, 3. Now, is 3 less or equal to everything in that set? It is. Therefore, 3 is a lower bound. So 3 is a lower bound of 2370. In the end, the reason why is that 3 is less or equal to x for all x in 2370. How about negative 3? Is negative 3 a lower bound? It is. How about I don't know, 19? Yeah? There's a lot of lower bounds, right? Infinitely many of them. So, you know, in fact, all of this stuff is a lower bound, are individually lower bounds. So how about 23 itself? Is 23 a lower bound for that set? It is, because the definition of lower bound does not require that point to be in the set itself. That's not required. You know, so even including that one. And so now, concerning the red set now, the set of all lower bounds. The set of all lower bounds for this set has a maximum. So the max. So if I say that x, big X, is the set of all lower bounds, of 2370, which is to say the red, then the maximum of x exists. The maximum of x is what? 23. And that concept is called the inf of a set. So a set that, if a set has a lower bound, if there is one, because there doesn't need to be one. For example, the reals, like all the reals, they don't have a lower bound. But if the set has any lower bound, then it must have a greatest lower bound. And that greatest lower bound is called the infimum. And if a set has an upper bound, if the set of upper bounds is nonempty, then that set of upper bounds must have a minimum, and that's called the supremum. Okay, so then that's an analogous property that the reals have, called completeness. Okay, so that aside, so well, I'll say it like this. The way that you would write it is like this: infimum of 2370 is 23. So even though that set doesn't have a minimum, it has an infimum. Okay, good. Now we embark on the place that causes very much strife. Okay, this is well, we're about to say something that really twists the knife. It's disturbing. Most students seem to not like it. All right, with that warning, here we go. I'll say that in the first place, let A, A, B, and N be in the naturals. A, B, and N be in the naturals. And suppose, and I'll say this, if N is equal to A multiply B, so N is that product, then what we'll say is that A is a divisor of N. Now, because multiplication commutes, that means that by necessity, what else is true? Yeah, B also is a divisor. Okay. Now, the way that we're going to write this, is we're going to write now in other textbooks. Very often, the way that this one is written, A is a divisor of N, is you write A and then a vertical bar and then an N. And I really think that this is a disservice and a bad thing to do. So rather than that, I'm going to write it like this. So it's that same vertical bar, except I've written a less than over it. So A is a divisor of N, B is a divisor of N. Good? So for example, I have a question. So what this is that in the same way that less than is a predicate, it can be false or true. So as this one, I could ask, is it the case, is this thing that I've written here false or true? That's true, right? It's the statement is to a divisor of 10. So it is. So this is true. And the way you can, establish that it's true is because, in fact, 2 is equal to 10 is equal to 2 multiplied by 5. All right. How about 3 divisor of 10? Now this is false, right? It's false because there's no natural that you can multiply by 3 to get 10. Okay. How about 2 a divisor of 0? Is this true? Or is it false? So looking at the definition and this equation, which one is which symbol is 2 playing and which symbol is 0 playing? In that equation. 0 is in. So we're asking, we're asking, is this true? And the question is that, so 0 is equal to 2 multiplied by A. So can you solve this for a natural A? Is that solvable? Is there a natural that satisfies that equation? What is it? 0. So this is solvable. In the naturals with A is 0. So does 2 divide 0? It does. All right. Does 0 divide 0? I'm not asking, can you do 0 divided by 0? That's not my question. What I'm asking is 0 a divisor of 0? Yes, because in the end, all I'm asking is that concerning this equation, is there a solution? Yeah, yeah, but I just need one, right? I just need one, so that's true. Wait, so this is disturbing me. So wait a minute. How about does 3 divide 0? Yeah. What about 2370? Is 2370 a divisor of 0? It is, isn't it? Okay, so wait a second. So if I ask you, and we're coming to the point, and this is the point so we're racing the clock and coming to the point where things get disturbing. Suppose I say list the divisors of, say, 12. You know, that's something that you could do in grade school, right? So they always come in pairs. So like 1 is a divisor, and then what's the counterpart of 1? They always come in pairs? 12, right? And then 2 is a divisor and its counterpart, 6. 3 is a divisor and its counterpart, 4. And then sometimes if the natural happens to be a square, happens to have a natural square root, something will be its own counterpart. Like 36, the counterpart of 6 is 6, right? So we could do that. So because of that, how about this? Does 1 divide n? Is 1 a divisor of n? For any natural? It is, right? And for that matter, so this is true. And n, is n a divisor of n? Yeah. And when it's the case that those are the only divisors, those numbers are special, and we call those what? Prime. Okay, so now the reason why I'm writing less than, that less than symbol, is because what this thing does is it defines something called the division order. So it's saying that you know, it allows you to put the numbers in order. Now it's different than the linear order. The linear order on the naturals is this one, that you know, you have 0 is less than 1, is less than 2, is less than 3, is less than ... So when you say minimum, for example, when we said minimum on all these pages, all these previous pages, we were referring to this order. So what's the minimum of the naturals? It's 0, right? The minimum of the naturals is 0. What's its maximum? There isn't a maximum with the linear order. But now, because of this, because n is a divisor of 0 for all n, and because 1 is a divisor of n for all n, that means that according to this order, the division order, what is the least natural? What's the minimum according to this order? It's 1. So the minimum of the naturals according to this order is 1. What's the maximum? The maximum of the naturals. What's the greatest of all naturals according to this order? It's 0. So I want to stress to you before we leave just how surprising and twisting this is to your intuition, maybe. In the linear order, the minimum is 0, and there's no maximum whatsoever. In the linear order. In the division order, the maximum the maximum not only exists, but it's actually the minimum in the linear order. And the minimum is now 1. So we're gonna continue the conversation here later, but try to think about that.